Welcome to my presentation. So today I want to introduce one of my research. This research was done in last year. The title of my presentation is named as Seismic Sequence Boundary Attributes. Kurt developed a lot of seismic geometry attributes to highlight a coherence, like a coherence or like a curvature, to highlight the force, to highlight the fractures, to highlight like the channels. But I found that there's no attributes to highlight the sequence boundary. Then I think a little bit about this, and inspired by Kurt, I proposed the following attributes is named as seismic sequence boundary attributes. My presentation consists of three parts. So let's first say why I'm interested in the seismic sequence boundary attributes. In these slides, this photo is a world famous size sequence tracks defined by geologists. So the procedures of seismic sequence analysis is mainly identifying the unconformities and the corresponding correlative conformities. So by identifying unconformities and the correlative conformities, we can define the system tracks. From the system tracks analysis, we can find where we have a reservoir, where we have a source rock, and then propose the locations for well drilling. So from the definition of the seismic sequence analysis, we can find that there are three main tasks for the seismic sequence analysis. The first task in the seismic sequence analysis is defining the conformable successions of stratos. Within the stratos, one criteria is that there is no resolvable unconformities within one system tracks. So this is one criteria in the sequence analysis. Another criteria about a sequence package is that the stratos within the sequence must be genetically related. And I think the most important task or time-consuming task in the seismic sequence analysis is identify the unconformities and also the corresponding conformities. The conformities and the corresponding conformities together define our system tracks, or like LST, HST, or TST. If you have four system tracks, we have the another system tracks. So then the objective will become very clear to me. So we need highlighting the unconformities for our seismic data. At the same time, if we can find the corresponding conformities, it will help us to expedite the process of seismic sequence analysis. So my proposed idea is very simple. So this is a seismic section from the F3 seismic survey. So what I'm going to do, I'm going to define a set of referred seismic traces. The referred seismic traces is a location of the referred seismic traces is indicated by the vertical red curve. So each of the red vertical line indicate one referred seismic trace. So the referred seismic trace at the referred seismic trace location, I'm going to track horizons. For example, here, this is one example of the tracked horizon for this seismic referred seismic trace. So when I do the seismic horizon extraction, I use two criteria. The first criteria is we are going to track the horizons for each peaks of the seismic amplitudes. At the same time, I'm going to track the seismic horizons for each trough of the seismic amplitudes. So based on the seismic deep attributes, I can track the seismic horizons for each peak or trough or seismic amplitudes. The yellow curve demonstrate the extracted horizons for this seismic section under the constraint of the red referred seismic traces. And here it is another example about the extracted horizons for the referred seismic traces. If we compare these two extracted horizon, we can find that, for example, here, if the seismic seismic reflection events are parallel each other, then we can extract seismic horizons parallel each other. You guys can notice that on the left side, on the right side, because the seismic reflection events converged to one or two or several seismic events, then we have a convergence of extracted horizons. Similarly, for this for this seismic section, we can observe the thermal features. So what I'm going to do next is counting the seismic horizons passing to each of the seismic samples. You guys can notice that here we have some unconformity there, we have some degradation there. Then we have like a swamp of extracted seismic horizons. So on the right side here, we have parallel seismic reflection. Then each of the extracted seismic events are parallel with each other. So the next step is counting how many seismic horizons passing through each of the seismic samples. So, and here it is one example about all the extracted horizons overlaid with the seismic section. So each from this seismic section, we can notice that some of the sample may have low horizon passing through, but some of the samples of the seismic traces have several horizon passing through. So the next step is counting how many horizons passing through a certain seismic samples. And the figures on the left, it is the vertical seismic section, and the figures on the right, it is a normalized number of seismic horizons passing through each of the seismic samples. So then the seismic sequence boundary attributes is defined as the numbers of seismic horizons passing through seismic samples. So if we compare these two images, we can notice that here we can notice that the seismic sequence boundary attributes can highlight the unconformities at the same time the corresponding conformities. Here it is another example about the seismic and the corresponding seismic sequence boundary attributes. So based on the seismic sequence boundary attributes, we can define the seismic tracks much easier than before. So here it is one example. This is arbitrary seismic line within F3 seismic survey. We have this wheel, the wheel 1 and wheel 2. And we can notice that we have a lot of seismic tracks here. And based on the interpretation of the wheel logs, we can do some interpretation like this. So this image, it is the seismic sequence attributes. So the seismic sequence attribute, so the peaked horizon is based on detailed analysis of the wheel logs. And here it is a wheel logs. We can we conduct a very detailed sequence analysis using gamma ray, and we can notice that those are the seismic tracks, and they like TST, HST, LST, or FST. So those kind of seismic tracks, we have like horizon top there. According to the horizon top and the seismic time, we can define our seismic tracks like this. And in this seismic, within this vertical section, the blue color, it means causing up of seismic sequence package, and the yellow package, it means the dirty up sequence package. Then we can notice that the proposed seismic sequence attributes can help us to define the seismic tracks or the sequence packages. So to better illustrate the result, I'm going to draw some like afterlying within the seismic survey. And here it is a location of the wheels. So we have 3 wheels within the seismic survey. And here it is one seismic line. And we can notice that this yellow arrow indicates the maximum flooding surface. The maximum flooding surface by analyze the seismic reflection patterns and also the weir log data. So if we say the seismic sequence attributes, you can notice that the seismic sequence attributes can clearly detect the maximum flooding surface. So, and here is another example about the maximum flooding surface. Another surface for the seismic sequence analysis is the maximum regression surface. And here it is the location of the seismic section, the black curve. And the yellow arrow indicate the maximum regression surface by analyzing the seismic reflection patterns and also the weir log analysis, the gamma ray log. So we can notice that the seismic sequence boundary attributes can also clearly highlight the maximum regression surface indicated by the red the yellow arrows. So here it is one more example, and one more example. So the third example is about unconformity. So as I just introduced at the beginning of my presentation, the unconformity is very important to define the system tracks according to the unconformity and corresponding to corresponding conformities, we can define the system tracks. And this is the location of my seismic section, and the yellow arrow indicate the unconformities. So if we saw the result of my sequence attributes, we can notice that at the unconformity location, we have like a high value of seismic sequence attributes. So they are, and here, the red curve, it is in the interpreted unconformities. The black, the white and black indicate the values of the seismic sequence attributes. So based on the analysis, I'm going to draw the following conclusions. So the seismic sequence stratigraphy attributes can highlight the boundaries of the seismic tracks, both for the unconformities and the corresponding unconformities. And so we are expecting that the seismic sequence attributes can be used to indicate the reflection patterns within the system tracks. But the second one right now is still under cooking for the real application. I think I'm going to done this within sometime this month. So, and at the same time, I think the proposed seismic sequence of attributes will also highlight some of the parallel seismic reflection events. The parallel seismic reflection events may be not related to the sequence boundary, but the sequence boundary will be definitely highlighted by our attributes. So this is the end of my presentation. Now I'm ready to take any questions related to my presentation. Thank you.
Question. In your article, are you expecting like that the water sediment or jungle sediment? Because you find this guy that was very significant work on interpreting every horizon in a set. But it respects the stratigraphy. So is that part of the code? And what I know just thought and say that you haven't been find somebody with nice certificate and what are the differences between your code, what is already available version?
So let first me clarify your question. So you mean my extract horizon consider the timing of the sequence? So currently, this is a very good question. So in the real world application, we should consider about this. But in my code, I didn't consider the time relationship between different sedimentology or sequence packages. So I just simply extract a horizon and then summarize counting how many horizons passing through a certain time samples. Currently, we didn't consider that. Yeah, but this is a very good question. Probably in the future, we can improve our code to say, oh, the deeper horizon, and so it cannot crossing the younger horizon. So this is very good suggestion. So it's not really difficult to modify the code because if we have two horizons crossing each other, then we can delete one of them. Yeah, yeah. So thank you so much for the comments. Yeah, so we can do a comparison and say which one is better.
It's work with that.
So,
It's not my fault.
so yeah.
One question about that, are those horizons like propagated and forced to be propagated around all the volume?
Oh, this is a very good question. So right now, in fact, I'm doing a little bit cheating. So if I extract the horizon over the whole volume, that's the ideal case. This is a very awesome suggestion. But right now, I'm extract the horizon section by section. The reason is the computation cost. So after I extract the horizon section by section, then I do then I do a summarization and smooth over the 3D. The smoothing step, I didn't illustrate the smoothing step here. That's can help us to propagate my 2D extraction into the 3D dimension. So right now we are extract horizon on 2D section, not 3D, because the time cost. So if we extract the horizon on 3D, that's for the ideal case, it is very time consuming.